Greetings. We're going to do an energy math problem set, the first of hopefully a few many. Today we look at the power. P is equal to the energy times time is equal to volts times amps. And this is from electricity, otherwise known as V times I, the voltage times the current in amps. We also have to just have a couple of facts known, that the energy unit is joules, and a joule is equal to power times time, and that's coming from the above equation, power equals to energy divided by time. And energy in joules is also equal to watts times seconds. 1 watt is equal to 1 joule per second by definition, which is equal to 1 volt times 1 amp by definition. So when we take 1 watt and multiply it times 1 second equals 1 joule, just keeping that in mind for the conversion factors that we're using. So that gives us the energy use. 1 kilowatt hour is equal to 1,000 watts times 1 hour. Well, what's 1 hour? It's 3,600 seconds. So 1,000 watts kilowatts is going to turn into 3,600 kilojoules. Got to remember, 1,000 joules is the same as 1 kilojoule. Kilo means, by definition, 1,000. Other conversion factors, 1 calorie is equal to 4.184 joules of energy. So that's a common conversion factor you need to know. Another one is 1 BTU equals 1.05 kilojoules. That's thousands of joules. And that 1 therm unit, not to be confused with British thermal units, that 1 therm is 100,000 British thermal units as a conversion factor. In our first problem, we've received a bill of 1,355 kilowatt hours is what the statement is on it, and this is over a 30-day period. And they want us to find the energy in kilojoules over this 30-day period. Find the energy in kilojoules per day, basically taking the A answer divided by 30, and then given a rate of only $0.079 per kilowatt hour, find the total cost for this bill. So here's how we start it. We know that 1 kilowatt hour is equal to 3,600 kilojoules. So that's the first conversion factor that we're going to need to have. Now for answer A, since we're going to start with 1,355 kilowatt hours, so we're going to multiply this by the conversion factor of 3,600 kilojoules for every 1 kilowatt hour, and that's going to equal 487,800 kilojoules. And since this is 1, 2, 3, 4, 5, 6 decimal places, that's also 4.878 times 10 to the 6th kilojoules is the same thing in scientific notation. And notice we keep 1, 2, 3, 4 digits because we started with 1, 2, 3, 4 digits in scientific notation and number of digits that we can work with. So that is the answer, kilojoules over a 30-day period. So B, now in joules per day, we just have to divide by 30. So you take your answer above, 4.878 times 10 to the 6th kilojoules, and divide it by 30 days. And then what do? You can remove one of the zeros here. This becomes a 5. Take a 0 off here, so divide by 10 on top and bottom, and then 4.8 divided by 3. So that gives us 1.6, and then it's 2.6 times 10 to the 5th kilojoules per day is the amount of energy being used per day. And then C, since we have a rate on a kilowatt hours, and we have 1355 kilowatt hours, again multiplying by essentially a conversion factor, converting kilowatt hours into dollars. So that's 0.079, and notice only 2 significant digits on this, per 1 kilowatt hour. This is in dollars, not cents. And that is going to equal about 101.4895 on the calculator, which we need to round. This is going to be in dollars, and round. So how many digits? Well, here we are allowed 2 digits. Here we're allowed 4 digits. So we're only allowed essentially 2 digits in the answer. So the final answer needs to be $100 total amount of money. But that's not what's going to appear on the bill. The bill is going to use all the way to the penny. So the better answer would be $101.49 as far as what will appear on the bill, because computers just add the zeros and don't care about significant digits. In the second problem, we have a toaster that has 8 amps of current that it uses at 110 volts. And so we have to kind of remember power equals volts times the amps in current. And we want to find the power in watts. So just simply multiplying. So the answer for A is just going to be the watts is equal to 110 volts times 8 amps equals 880 watts. We also have to remember that this is also equal to 880 joules per second. We may have to use that later on. Okay, then for the B answer, calculate the energy in joules for 5 minutes of use. Okay, so if it's 880 joules for every 1 second, which is what this means up here, this quantity, joules per second, because it's watts. And so, but how many seconds are we talking about? 5 minutes. So we have to multiply by 5 minutes. So for there is 60 seconds in every 1 minute. And then we also have to multiply by the 5 minutes. And then so that's going to give us the total number of joules is what we're seeking in the problem up here. And so we can cancel out the minutes, cancel out the seconds, and we end up with an 880 times 60 times 5, and that's going to equal 2,000 or 26,400 joules of energy, which also equals 26.4 kilojoules. So sometimes the answer will be in joules, sometimes kilojoules, but what was asked for? Always point, what was asked for? It's going to be in joules. In our third problem, we have a 100-watt light bulb here, and it is 20% efficient. Yeah, that's actually pretty good for a light bulb if it's incandescent. Maybe it's another type of light bulb, because incandescents are like 10% efficient. In this case, we have a 20% efficient light bulb, and it's 100 watts. So now the first problem is, what's the total energy used in 12 hours? Well, for A, remember that energy is in joules, is what we're seeking. We have 100 watts equals 100 joules per second for every 1 second of use. And we're multiplying this by 12 hours. And so now we have a time. We're going to end up with joules, and that's what we're going to end up with. Okay, so we just have to convert 1 second in 12 hours. So maybe it's faster if we just go ahead and convert the 12 hours. So 12 hours times 60 minutes per hour. This always goes over 1 when you start conversions, times 60 seconds for every 1 minute. And this is going to give you 12 times 60 times 60 seconds. So we've just converted 12 hours, canceling the hours, canceling the minutes, and ending up with seconds. And this value comes up to be 0 and 0, 36 times 12. And then you just keep working your way down, especially if you do it by hand instead of by calculator. 0, 0. And this is going to be 72 plus the 36, 0, 0, 0 for the 10. You add those two together, and you come up with 2, 3, and 4. 43,200 seconds. So we've got that in the seconds category. So now we just have to go on back and multiply 100 joules for every 1 second times 4,320 seconds. And that's going to give us a total of 432,000. And you count back 1, 2, 3, put a comma in, 1, 2, 3, put a comma in. But that's a total of 4.32 times 10 to the 6th joules of energy for the answer in A. This is also the same as 4.32 times 10 to the 3rd kilojoules. Now that was for the A answer, how much energy is used in 12 hours. You got that done. Now calculate the light energy and the heat energies that are being produced in these same 12 hours. Well, we have to look up at 20% efficient. That means 20% is used for light and 80% goes to heat. So we take this information and use it in these two problems. So essentially 1/5 of 20% equals 1/5. So for the B part, let's put that over here. So for the B part, so when you multiply it by 1/5, and what do you get? Just divide by 5. So that's 0.8, and then carry the 3, and that would end up about 6, times 10 to the 3 kilojoules, which can also be stated as 860 times 10 to the 3 joules, or 860,000 joules. These will all be correct answers. Now the C answer is, to get that, well, gee, 20 to 80% up here. There's a couple ways of doing it. 20 to 80%, that's just 4x. So we can multiply this answer down here and just multiply this times 4, and that's going to equal to 0, 0, 0, 0. 4 times 6 is 4, carry the 2. 4 times 8 is 32, and we've carried the 2, so that's 34. So we end up with 3,440,000 joules of energy. Now in the final answer that we need up here, now we need to calculate and convert total energy into kilowatt hours. So we've got a total of 12 hours to start with. So we need to go on back. So we'll put D over here. And we know that the kilowatt hours is going to be equal to a kilojoules in some fashion, some sort of in that range. which is also going to be equal to some sort of watts times time. So we just have to put in the right calculations. So let's start down here. So we're going to convert 100 watts and change that to 0.100 kilowatts to start off with, and then times hours, times the hours. What's it? 12 hours. And what do you end up with? You end up with 1.2 kilowatt hours as the final answer here. That goes back to the question D. Okay, in our fourth problem, we have a clothes dryer at 4,000 watts. And it turns out that electric dryers do use the most energy when they're in operation, but actually that's not the most use. Refrigerators, of course, use energy all the time to keep food cold and uses more energy. But for large families, it looks like it's got a few folks in it because there's 5 loads being done every 4 weeks, and that each load takes 1 hour of time. So the first thing we want to do is, okay, we're given this information before we even answer any questions. What does this look like? So 5 loads every week times 4 weeks equals 20 loads. And we also multiply this by 1 hour per load equals 20 hours of total work time. And this is all being done at what? 20 hours at 4,000 watts, which again is equal to joules per second, keeping that in mind. So we go back to A now and calculate the energy used in joules and in kilowatt hours. So what do we have? We have watts and we've got time. So that's the first thing we need to do is we need to be able to work in seconds, joules per second, and this is hours. But we have kilowatt hours. So how do we do this? Okay, we've got watts and we've got hours. Can we calculate kilowatt hours? Okay, so if we have 4,000 watts, which is equal to 4 kilowatts, okay, now we take that and then we multiply by the 20 hours equals 80 kilowatt hours. So that's a simple solution. So once we got the kilowatt hours, and we know that 1 kilowatt hour is equal to 3,600 kilojoules, because there's 3,600 seconds for every hour. So we just have to take this 80 here and take this 80 kilowatt hours and multiply it by another conversion factor of 3,600 kilojoules for every 1 kilowatt hour. And we end up with 0, 0, 0, and then 8 times 6 is going to be 48. Carry the 4. 8 times 3 is 24. Carry the 4 is 2 to 8. And this is all going to be in kilojoules now. So this is 2.88 times 10 to the 1, 2, 3, 4 kilojoules. Since the answer is originally asking for joules, again, we need to convert this to 2.88 times 10 to the 7th joules. Okay, in answer B, we have a cost, and this is going to be 0.0758, or about a little over 7.5 cents per kilowatt hour is what the charge is. And now we've just got times the 80 kilowatt hours. And so this comes out to a total of $6 and about 6 cents. In number 5, we have a gas bill, I forgot the T in there, states that we have 110 therms of energy being used over a 30-day period of time. So we need to convert the therms into kilowatt hours. Okay, so we have to go back to the original units of conversions. We have to know that 1.05 kilojoules for every 1 BTU. We also know that there's 1 calorie for every 4.184 joules. Just kind of write down some of these things just in case. And we know that we have 1 kilowatt hour is equal to 3,600 kilojoules. So given that as a basis, let's go down to start the answers. So we always start with the conversions. 110 therms. So let's convert that to BTUs. So this is 100,000 BTUs for every 1 therm. So that conversion is made. And then we know that there is 1.05 kilojoules for every 1 British thermal unit. And at least that gets us into kilojoules. And then we've got to multiply this by 1 kilowatt hour for every 3,600 kilojoules as another conversion factor. So when we multiply it all together, put all the numbers together, 100 times 100,000 times 1.05 times 1, but let's just leave that out, divided by 3,600. And the units end up here, since therms cancel, BTUs cancel, kilojoules cancel. We're now left with kilowatt hours is what we want in the end. So just a matter of calculus. Now on a calculator that might be easy, no calculators are allowed. So how do you deal with this? By hand. So the first thing you can do is start canceling anything else. Oh, by the way, this is not 100 therms. Sorry, this is 110 therms. Let's get that corrected. 110 therms. So we can start crossing out zeros. So cross out this zero, and 2 zeros get crossed out there. Now, can we approximate? Okay, so we know divide by 36. We know that 36 times 3 is what? Is 8 and 108. That's close to 110. So can we just approximate this? Since we only have, what do we have? We have single digits and conversion factors, 1 BTUs and 1.05. We have 110 therms. There's only 2 digits there. So maybe just a 2-digit answer is good enough. So for this, if you're just seeking 2 digits, so 110 divided by 36 is approximately 3.0 something, then we can just leave it like that. And then we use that, and we end up with 3.0 times 4. Remember, there's only 1, 2, 3 zeros left. So times 1,000 times 1.05 kilowatt hours. And then we take this one and we say, oh, okay. We just multiply the 1.05 times 3 and end up 3 and let's say 3.1. Actually 3.15, and the 3.5 moves up to 3.2. So 3.2 times 1,000, and that is equal to 3,200 kilowatt hours total time. Now the B answer, where we have, again, a total of $88.78 total. Okay, and we divide this by a total of 3,200 kilowatt hours. And then we need to simply take dollars per kilowatt hour, and that's the rate we're looking after. Okay, so now we've got it. We just now have to calculate it. Again, calculate on the calculator is pretty easy, but how do you calculate this by hand? Well, let's see. Well, wait a minute. Before we do it by hand, can we first divide everything by 8? Oh, it's going to be pretty close. So let's go divide by 8. So that's 1.0, and then maybe close to a 9. Well, we have to need 2 digits, so we'll just leave it like that, approximately. Divide by 8, and we end up with 400, because 8 times 4 is 32. So, and $11 divided by 4, maybe that will work. That's dollars per kilowatt hours. Still carry the units. Okay, so we have $11 divided by 400. Again, we can maybe divide that by 2, make it simple. So we end up with 5.54 divided by 200, and then divide this by 2, and that ends up being 2.7, and then carry the 1. It's going to be another about 7 or 8 there, and divided by 100, and so that's going to be approximately 0.0278. This is going to be dollars per kilowatt hours, but again, we only start with, even though we start with 4 digits over here, we really only have 110 therms. That's only really 2 digits up there. So this rounds to $0.028 per kilowatt hour as a final answer.